In this video, I discuss about ventilation and ventilation coefficient and also solve a problem. This video is in continuation of my earlier three videos, video number 124, 125 and 126. Air pollutants travel through the air and reach receptors. And during this transportation, sometimes it is transformed. The pollutants get transformed in the atmosphere. The effect of pollutants that reach the receptors depend on how close they are to the pollution source, how the air moves, how much pollutant concentration there is, how high up it is released, that is the stack height, how long it stays in the air, and finally how sensitive the receptors to the pollution also matters. So the location, height, duration of release, amount of pollutant release, behavior of the pollutant, wind speed, as well as the sensitivity of the receptors are important to determine the effect of pollutants on the environment. If air movement along with a continuous pollutant source is slow, pollutant concentration in the plume moving downward will be much higher than they would be if the air are moving rapidly past the source. If polluted air continues to have pollution added to it, the concentration will increase. The pollutants do not just stay in one small area, they are distributed into larger volume of air depending on factors like wind speed, the height of the release, the height of the stack, and how long the pollution is being emitted. Even with significant air motion and subsequent help to spread the pollution, pollutant can still accumulate in certain areas over time if there are many pollution sources. Here, this is a picture, a diagram, and you can see that this is a factory and this is a stack and this plume is rise. So I describe this diagram. So plume rise is the upward movement of pollutant released into the atmosphere from a source, and this is transport and dispersion, that is movement and spreading of pollutants through the atmosphere influenced by wind and other atmospheric conditions. Then the transformation means the chemical and physical changes that pollutant undergo while in the atmosphere. Washout means removal of pollutants from the air by precipitation, it is rain, and fallout means the settling of pollutants back to the earth's surface, often due to gravity. Impaction is the process by which pollutants are deposited on the surface of receptors like building, trees, or soil, and this is a monitoring station for observation and measurement of pollutants. So this is the atmospheric role in air pollution. Now, ventilation coefficient. It is a meteorological parameter that represents the ability of the atmosphere to disperse pollutant. It is calculated as the product of the mixing height or mixing depth and the average wind speed within the mixing depth. The average wind speed within the mixing depth, and generally expressed in meters square per second. So this is the formula: ventilation coefficient is equal to mixing height into wind speed. The significance of ventilation coefficients are: a higher ventilation coefficient indicates good dispersion conditions, meaning pollutants are quickly diluted and spread out, reducing air pollution, that is improving air quality and reducing localized environmental and health impact. And a lower ventilation coefficient suggests poor dispersion, leading to pollutant accumulation near the surface and worsening air quality and a great risk to the environment and health impact. And mixing height, wind speed, and the seasonal and diurnal variation are the factors which affects the coefficient, ventilation coefficient. So the higher mixing height allows better dispersion, that is lower mixing height is better, the less dispersion. Wind speed, if high wind speed helps spread out pollutants, low is the adverse, and the low ventilation coefficient is common in winter and at night due to temperature inversion. So during that time, the ventilation coefficient is less. That's why air pollution is more. So if there is any range for ventilation quantity for air quality, yes, if ventilation coefficient is greater than 600 meters per second, then it is favorable condition for dispersion of pollutants. But if it lower than 6000 meters square per second with average wind speed less than 5 kilometer per hour, which is unfavorable for dispersion of pollutants. So this is an indicative table to know the dispersion condition and air quality implication based on the uh, ventilation coefficient. So you can see if it is greater than 6000 meters square per second, so the excellent dispersion and good air quality. 4000 to 600, it is good air quality unless emissions are extreme. 200 to 4000, it is moderate, some accumulation is possible under high emission. 1000 to 200 is low, poor dispersion, pollution may build and observed in winter and stable atmospheric condition. And less than 1000 meters square per second is dispersion condition is very low, so it's a high risk of smog, fog, severe air pollution. So in practically what we have observed that in winter in Delhi, this ventilation coefficient is less than 1000 meters square per second. So smog and severe air pollution is observed. And at coastal cities with strong winds, this coefficient is greater than 6000 meters square per second. So good air quality. Now we're going to solve a problem, and I suggest at this juncture to revisit to see my earlier video number 126 on mixing height, and then it will be good to understand this problem. Suppose following at the atmospheric altitude versus temperature data collected, you can see that at ground level temperature is 20 degrees centigrade, and as we go up at 100 degree interval, that is 100, 200, 300, 400, 500 and 600 meter, the temperature of the atmosphere will be 18 degrees centigrade, 16 degrees centigrade, 15 degrees centigrade, 16 degrees centigrade, 17 degrees centigrade and 18 degrees centigrade respectively on the altitude. You can see here. So you have to calculate first the mixing depth. Second, if there is a stack, 100-meter height stack emitted at 20 degrees centigrade, so and the rate is dry adiabatic lapse, then how high would you expect the plume to rise? And third, to calculate the ventilation coefficient at mixing height, that is mixing height with wind speed 8.7 meter per second, halfway to mixing height with wind speed 7.6 meter per second, and at the weather station anemometer reading 10 meter from the above ground level, 4 meter per second wind speed. So you have to calculate 3 ventilation coefficient, but this, for this calculation we have to identify mixing depth or mixing height first. So the first question is what would be the mixing depth, and this is our graph, and you can see this is the table. So I plot the atmospheric temperature at 0 meter 20 degrees, so I have to put one here. At 100 meter it is 18, so at 18 it was here, and second is 16 at 200 meter here. So accordingly I plotted the all 8 points, 7 points, yes, 7 points here. So if I just draw the line, just draw it hand. Oh, so it is not great actually. Just hand draw. So this is the temperature profile here, and from this point, that is from this point, if I use a dry adiabatic collapse rate at -1 degree centigrade per 100 meter of altitude, so this would be the dry adiabatic collapse rate. And if I join this line, you can see that this position, that is 400 meter height, is the mixing depth here. You can see, so this is the mixing depth projecting from 20 degree centigrade at 0 meter at slope -1 degree centigrade per 100. So this is our mixing depth. Now what is our second problem? Second problem is here, and I just plot it again here and just draw this line only. Now our stack is 100 meter and its emitted gases is 21 degrees centigrade. So I put our stack here at 100 meter height. So this is, and it emits gases at 21 degrees centigrade, yes, here, and it follows dry adiabatic collapse rate, that is, and 200 meter it will be 20. So accordingly if I plot this, so this is the rate, and if you see that this point, if I joined this line, you can see, so this is, that is 500, this is 500, you can see 500 meter. This is the point where a pollutant, a plume height can go. So plume rise projecting from 21 degrees centigrade at 100 meter at slope -1 degree per 100 meter, it is 500 meter. So I get the plume height of 500 meters. So this is my mixing height for calculating the problem number 3. So we have got the mixing depth, that is 500 meter, and wind speed is here. So the ventilation coefficient at 500 meter would be, so this, and at halfway, so for halfway it is 250. Wind speed is given here, mixing height is fixed 500, and accordingly ventilation coefficient is this. And for ground level from 1 meter height, this from 10 meter heights, and it is 200. meters. So this is the ventilation coefficient of different height. But if you have this is a three problem at a time, but if generally you only problem one or problem two or problem three comes, so we have to identify one ventilation coefficient. But if the scenario is like that, you got three wind speed, then you have to calculate average wind speed. So this is our data. So you have to calculate the average wind speed here. So it is uh, 6.8, and accordingly the mixing height is 3400 meters square per second. So for further reading, you can use this reference. Thank you for watching this video.